Okay, good evening students. I am going to start the class and you listen very carefully, right? And the today topic is the total energy of a satellite. How to find out the total energy of satellite that we are going to discuss. You listen very carefully. Do you know what is the formula for the orbital velocity and escape velocity? Do you know the formulas for the orbital and escape velocity? Yes, you know, orbital velocity means it is the velocity of satellite to revolve around a certain planet. Now I am going to explain the total energy of satellite. What is the total energy of satellite? Total energy of satellite. How we can find out the total energy? Total energy of satellite means it is the sum of potential energy and kinetic energy. Is it clear, students? My voice and everything, right now? Okay, students. Right. Let us go for the. This is the Earth. The Earth radius we can take as capital R, and one satellite is revolving around the Earth at certain height from the ground. This is the height at which the satellite is revolving around the ground. Okay, this is the satellite mass is small m, and this is the planet. Okay, the planet mass is capital M, and the satellite is revolving around the planet like this. Satellite is revolving. Now our question is that the satellite has some speed at here, right? Orbital speed it is called. We know the formula for the orbital speed. And now this is satellite total energy I am going to derive. For that, what you have to do it here. First of all, we have to write the potential energy of satellite. What is the formula for the potential energy? We derived previously. This radius of the orbit we can consider as a small r. Okay. Potential energy of satellite. What is the potential energy of satellite? Potential energy formula we know. Potential energy between the two objects we know is minus G capital M small m by R. What is capital M in this? Mass of planet. Okay. What is a small m? Small m is the mass of satellite which is revolving around the planet. Right? And R is what? R is the distance between the planet and satellite, or we can take it as the radius of orbit also. Radius of orbit in which the satellite revolving. We can also write the radius as a smaller from the figure capital R plus H also we can write. Then this is the potential energy formula. Capital R is this one, radius of the planet. Okay, capital R is the radius of the planet. Capital R is radius of planet. H is the height of satellite from the surface of Earth. Total radius of orbit. This is the orbit, right? This is the orbit around that. In that orbit, the satellite is revolving. This is the satellite, right? This is the satellite. Now we want the potential energy formula we derived. Next, I want the total energy. Total energy is the sum of potential energy and kinetic energy, right? If you have any query, you write in the chat box. Students, is it clear now? Okay, students. Now, potential energy is completed. Next, I want the kinetic energy of satellite. How to find out the kinetic energy of satellite? Okay, satellite of mass small m revolving around a planet of mass capital M with orbital speed v naught, right? Then the kinetic energy of satellite I want. How to find out the kinetic energy of satellite? The kinetic energy of satellite formula, general formula for the kinetic energy, you know, half mv square. I want the satellite kinetic energy. That's where satellite mass we have to write. Satellite mass is small m and planet mass is capital M. Okay, right? Satellite velocity is v naught. Do you know formula for the orbital velocity? Satellite velocity is the orbital velocity. Do you know the satellite velocity formula? I think you know right now. Now of m into, we write v naught formula as under root g capital M by r plus h. You know this one, orbital speed formula in the last class we derived, right? Gm by r plus h we write as a small r. Small r is the radius of orbit. If you substitute it here, then v naught we write as under root g capital M by small r whole square, right? And if you simplify this, we will get the kinetic energy as half m into this, we write as square root will cancel, then we will get as g capital M by r. Then finally we will get the kinetic energy of satellite as g capital M small m by r. This is the kinetic energy of satellite. Okay, understood students? If you not understood any step, sir, this step is not understood, you right. Okay, Ashish Gagarai, clear, thank you. And now the next one is the total energy of satellite. I want to find out total energy of satellite which is revolving around the certain planet. Okay, total energy of satellite is the sum of potential energy and kinetic energy, right? Total energy is the sum of potential energy and kinetic energy. Then we will get the total energy as the potential energy is minus gmm by r, and the kinetic energy formula is what? The kinetic energy is G capital M small m by 2 into R. Here 2 is missing, right? G capital M small m by 2 R we write. Now, if we simplify this, we can common the G capital M small m by R. You will get to minus 1 plus 1 by 2. If you simplify this minus 1 plus 1 by 2, you will get minus 1 by 2. That means total energy we will get as, okay, minus, if you simplify this one is, you will get minus 1 by 2 minus 1 by 2 into gmm by r. That means minus 1 by 2 into gmm by 2r we will get. This is the formula for the total energy of satellite, right? Okay, we derived the potential energy, kinetic energy and total energy formulas right now. You see here, this is the formula for the potential energy of satellite, and this is the formula for the kinetic energy of satellite, and this is the formula for the total energy of satellite. Now let us see what is the relation between the kinetic energy, potential energy and total energy. Now for the purpose, you listen very carefully. It was a very simple, I'm going to explain. If you have any query, write in the chat box. Okay, right. Now I am going to explain one thing. Just now we derived the formula for the potential energy and kinetic energy also and total energy. I want the relation between the potential energy, kinetic energy and total energy. For the purpose, what we have to do it here. Right. Let us start. Very simple. Right. I want the relation for that potential energy formula. What you got? Potential energy is equal to this we write in the note. Okay, in the note we can write. Potential energy formula is what? Minus gmm by r. Right. Kinetic energy formula. What you got? Gmm by 2r. Potential energy formula. What you got? Total energy formula. What you got? Minus gmm by 2r. I want the relation between these. Okay, relation between the total energy and potential energy. This we write as total energy is equal to, okay, from above equations. From above equations. From above equations we can write something, that is total energy is equal to, you see the total energy? Total energy formula is minus of gmm by 2r. Gmm by 2r is the kinetic energy. Can I write like this? Total energy is equal to minus into kinetic energy remaining. This part is the kinetic energy. Is it right? We can write like this. Total energy is equal to minus of kinetic energy. Total energy we can also write in terms of potential energy. Further, what I will do it here, I will do like this. Okay, total energy is equal to this one minus gmm by 2r. I will write like this. Okay, I will write like this. I will write 1 by 2 to a side. Okay, 1 by 2 to a side. Remaining is what? Minus gmm by r. In this total energy formula, we can write like this. That is 1 by 2 into minus gmm by r we can write. This minus gmm by r from the figure is potential energy. That means total energy is equal to half of the potential energy. Right? You no need to remember the relation between the total energy and kinetic energy, total energy and potential energy. Just you have to remember the formulas of potential energy, kinetic energy, total energy of satellite. Then automatically while solving the problems, we can use that settings. Okay, right? And I got the total energy, kinetic energy relation, total energy, potential energy relation, potential energy, kinetic energy relation. I want. And for the purpose, kinetic energy is equal to write like this. Kinetic energy is equal to half of the half into remaining part is what? Gmm by r. Gmm by r we can write as minus of potential energy. Then we can write as kinetic energy is equal to minus half potential energy. These are the relations between the total energy, kinetic energy, total energy, potential energy, total energy, also kinetic energy and potential energy. Right? Okay. Right now let us go for the continuation. And this is about the total energy of satellite. And the next I am going to derive the formula for the time period of satellite which is revolving around certain planet. Okay, right? I'm going to erase this. Next topic is the time period of satellite. How to find out the time period of satellite? Right, the next one is the time period of satellite. Time period of satellite. What is the time period of satellite? Time period means what? Time taken to complete one revolution, right? Time required for a satellite to complete one revolution, one revolution around a planet, around a planet is called as time period, right? This is the time period. This time period I want to find out how much time required for a satellite to revolve around a planet. The time on what factors it depends. Then how we will derive that formula? It was very simple to derive. Just we will take this as one planet. Okay, this is the one planet. The planet mass we will take as capital M. The planet radius we will take as capital R. And at a height h, at a height h from the surface of Earth, at a height h from the surface of Earth, one planet is revolving. Okay, revolving in particular orbit. Like this, it is revolving. This same diagram just now we drawn. The diagram only again I am drawing. Okay, right. Now you see here, this is a satellite, and the satellite speed we can take as v naught, and satellite mass is small m. Okay, right. The radius of orbit is small r. Now the same thing, the time period formula is what? Time period is nothing but time to complete one revolution. Okay, the time period formula we write like this. Time period is equal to, that we can take as a t, that we can write as distance by speed we can write. Time is equal to distance by speed we write. What is the distance traveled in the one revolution? The distance traveled in one revolution is equal to distance traveled by the satellite in the one revolution. Time period of satellite, no? Distance traveled in the one revolution we have to write. Can you anyone write in the chat box what is the distance traveled in one revolution? Write in the chat box. Distance traveled in one revolution. Is it 2 pi r? Is it right? Circle length 2 pi r. What is the speed of this satellite? V naught. Okay. But we know formula for the V naught. But V naught is equal to, V naught is the orbital speed, right? V naught is the orbital speed. What is R? R is the radius of orbit, right? Radius of orbit. In one revolution, the distance traveled by the satellite is equal to circle length, circumference, 2 pi r we write. Then time period formula we write is 2 pi r into by V naught we have to write. What is the V naught? V naught is the orbital speed. You know formula for the orbital speed? In the last class we derived. If you want, you can refer. That is the orbital speed formula is under root of gm by r plus h. But we are taking that r plus h is smaller from the figure, then we will get like this, that we have to simplify 2 pi r into under root of r by gm we have to write. This r we can take inside, then we will get 2 pi into under root of, when r goes to the root, okay, it will become r square into r by gm we will get. Then the time period we will get as 2 pi under root of r cube by g capital M we have to write. What is capital M in this? Capital M is the mass of planet. Is it right? Mass of planet. Small m is the mass of the satellite. Small m is the mass of satellite. Okay, if you have any query, you write in the chat box. But from figure, we write like this. But from figure, we write small r is equal to r plus h, we write. Then we can write like this. That is, t is equal to 2 pi under root of, this is small r we write as r plus h whole cube by gm we write. Okay, this is the equation for the time period. From this equation, we write one thing. Either we can use this one or this one. From above equations, we write one thing. That is, I will explain. Okay, I'm going to take this to a side. Right, let us go for the continuation. That is, from above equations, we write one thing. That is, square of, you can square it, t square. You will get 4 pi square r cube by t square is equal to what you will get, tell me? 4 pi square into r cube by gm. That means from this we write like this, t square proportional to r cube, square of time period of revolution is directly proportional to the cube power of radius of orbit. This is just similar to the, this is the, just like it is a proof of Kepler's third law, law of periods, right? Okay, and this we can also write like this. And next one case I will explain, that is if satellite is close to the surface of earth. If satellite close to the surface of earth, satellite close to the surface of earth, then what is its time period? Okay, if any satellite close to the surface of earth, then what is its time period? Then we know time period formula in the last equation from this, 2 pi under root of r cube by gm, but smaller is capital R plus h, we can write r plus h whole cube by gm we write. But here I am taking that the height is very much less. Satellite is close to surface of Earth means height of satellite from surface is less. H is less means then R plus H we can write as R only because H can be neglected. H is neglected. Okay. H we can write nearly 0 comparing to the R because R value is very much high. This formula will be changes like this 2 pi under root of R cube by GM we will get. But one thing we know, what is the relation between the small g and capital G? Can anyone write in the chat box what is the relation between the small g and capital G? Or what is the formula for the acceleration due to gravity on surface of Earth? Acceleration due to gravity on surface of Earth formula. On surface of certain planet formula. Can anyone write? We know. Yes. Students respond. What is the acceleration due to gravity on surface of Earth? But we know acceleration due to gravity on certain planet we write like this: G is equal to Gm by R square. You know this? This is the acceleration due to gravity on certain planet. This is a planet whose radius is capital R and mass is capital M. This is a planet, right? And the satellite is the height is h. The satellite is revolving at very less height. The satellite mass is small m. Now, from this acceleration due to gravity on surface of Earth formula is G equal to Gm by R square. From this, Gm is equal to Gr square. At this we substitute in this equation, then we will get as 2 pi under root of R cube by Gm we write as Gr square. Then we will get as time period is equal to 2 pi under root of, right, R by G we will get. You substitute the values of, in case of Earth, I want to find out the time period of Earth satellite. Okay. In case of Earth, in case of a satellite, in case of a satellite revolving close to the surface of Earth. If any satellite revolving very close to surface of Earth, then Earth radius is what? 6,400 kilometers, right? This is the radius of planet we have to take. R is the radius of planet, right? Radius of planet, not satellite. Okay. And now 6,400 kilometers in case of Earth into 10 to the power of 3. G is the 9.8 meter per second square, but we can take for our convenient and easy simplification. I will take it as 10 meter per second square, and you simplify it and you substitute the values, and you will get the time period is 2 into pi value is 3.14 under root of R by G. R is 6,400 into 10 to the power of 3 by G value is 10. If you simplify this 6.28 into, you will get as this, you can simplify 10, this 0 will be cancelled, and this you will get 800, and after simplification you will get some value that is 5028 seconds. 5028 seconds. If you convert into minutes by 60 you have to do, you will get nearly 8.4 minutes or 1.4 hours. Okay, if satellite is very close to Earth, then the satellite will complete one revolution with within 1.4 hour. Okay, right. This is about the time period of satellite. Now let us go for the next topic, that is the geostationary satellite. I am going to explain the geostationary satellite. There are two types of satellites are there which are revolving around the Earth, and about that two satellites I am going to explain now. One is a geostationary satellite, and next one is the polar satellite. What is geostationary satellite and what is polar satellite? We derived the time period formula. Next I am going to derive the, I am going, not derivation, theory part I am going to explain. That is the, that is about geostationary satellite and One more is polar satellite. Let's start. What is geostationary satellite and how it will works, and that I am going to explain. Okay, that you listen very carefully. This is very important topic. Geostationary satellite. Geostationary satellite. Geo means earth. Stationary satellite. When you will see from earth, that satellite appears rest. Stationary means rest. Okay, geostationary satellite. Geostationary satellite means from geo, if you will see the satellite, then it appears at rest. That is geostationary satellite. What is the definition of the geostationary satellite? I will give the definition. A satellite, a satellite a satellite whose period of revolution, a satellite whose period of revolution is equal to the period of rotation of earth is called as geostationary satellite. Okay, what is geostationary satellite? Geostationary satellite is a satellite, right? It is a satellite. And how it will be revolves? I will explain very carefully you how to hear. This is the earth. What a diagram. Again I will draw. Try to understand the definition of geostationary satellite. Okay. Right now geostationary satellite means that will be revolve around the earth. This is the earth. Earth rotates about its own axis. You know this one? Earth rotates about its own axis with some speed. Earth rotates about its own axis. Is it right? Earth mass capital M and Earth radius is capital R. Earth rotates about its own axis. You know that one. And this geostationary satellite means it will be revolves like this. We will draw the orbit. This is the orbit in which the geostationary satellite will be revolves. And the satellite I will draw. This is the satellite. And its speed is V naught. And its distance is smaller. Okay, right? Like this, the satellite will be revolves. This is the geographical axis, right? This is the geographical axis, and then the plane which is it is the satellite revolving around the Earth. That is the geographical plane. Okay, right? And it should observe the earth, the satellite that appears at here. From here, if you will observe, the satellite appears at here. From here, if you will observe, the satellite appears at here. That means satellite always appears in front of you. What do you think that the satellite is always at rest? How it is possible? How it is possible? How it appears at rest? When we will see from the earth by using telescopes. When you will see the satellite by using telescope, that satellite appears at rest, not moving, right? Why it is appears at rest? Because actually the earth rotates about its own axis. For the earth rotation, for one rotation, how much time requires? Can anyone tell? Earth rotates about its own axis, how much time required to complete one rotation? How much time required to complete one rotation for the Earth to rotate about its own axis? Earth rotates about its own axis. In order to rotate, what topic Jaya Boy I require? Once again, I am asking one question. Right? Earth rotates about its own axis. How much time required for the Earth to complete one rotation about its own axis? That I am asking. What is your question? You can ask, and what is your doubt? You can ask. Okay, what I have to explain once again that you can tell. Right? Okay, let us start. And here, Earth rotates about its own axis. You see, Earth completes one revolution, one rotation in 24 hours only. In one day, Earth completes the one rotation about its own axis. That is called as the period of rotation of Earth. Okay, you see period of rotation of Earth. Cursor you should follow always. Period of rotation of Earth is 24 hours. And a satellite whose period of revolution, satellite is revolving, Earth rotating about its own axis. Satellite revolving time period of a satellite whose period of revolution, time period of revolution, that means satellite for one revolution how much time requires, that is equal to period of rotation of Earth. For Earth how much time required to complete one rotation, for satellite also the same time required to complete one revolution, then such satellite is called as the geostationary satellite. A satellite whose period of revolution is equal to the period of rotation of Earth, that is called as geostationary satellite. Okay, satellite is revolving like this at here. Satellite to complete one revolution sometime required, that is called as the period of revolution of satellite. Satellite to complete one revolution around the Earth, how much time required, that is called as the period of revolution of satellite. That should be equal to period of rotation of Earth. What is the period of rotation of Earth? Can anyone tell? Right? Period of rotation of Earth is the 24 hours. Right? Period of rotation of Earth. Earth completes one rotation about its own axis in 24 hours. Right? At that moment, what happens? Then Earth rotates and satellite rotates. Earth, how much? Earth completes one revolution in 24 hours. Earth complete one rotation in 24 hours. Satellite complete one revolution in 24 hours. That's why what happens when we will observe from here. For example, okay, this satellite is at here. Satellite complete one revolution and Earth also complete one rotation. Earth come to this location and satellite also comes to Earth. Satellite is moving. Earth is also rotating. That's why when the person comes to here, due to the rotation of the Earth, due to the rotation of the Earth, the person comes to here. At the moment, due to the revolution of the satellite, satellite will come to here. What this fellow will feels, again the satellite will be in front of him. Like this, Earth rotates and satellite rotates. That's why Earth always appears in front of him. That's why this fellow feels that satellite is at rest. Okay, right. This is the geostationary satellite. A satellite whose period of revolution, a satellite whose period of revolution is, satellite period of revolution should be equal to period of rotation of Earth. Period of rotation of Earth is what? 24 hours. A satellite whose period of revolution is 24 hours, okay, is called as geostationary satellite. Okay, is called as geostationary satellite. Geostationary satellite's time period is how much? What is the time period of geostationary satellite? That is 24 hours. In 24 hours, it will complete the one revolution. Next, geostationary satellite. Time period of geostationary satellite is 24 hours. Time period of geostationary satellite is 24 hours. And the geostationary satellite will revolve in equatorial plane of Earth. Geostationary satellite. Geostationary satellite revolve in equatorial plane. Equatorial plane. What is equatorial plane? This is the equatorial plane, right? Equatorial. For the Earth, equatorial plane, you know? Equatorial plane. Geostationary satellite revolves. Equatorial plane means this is Earth, means if you cut like this is equatorial plane, right? In the equatorial plane, it will be revolves. This is called as a geographical axis. It is an axis. Along this axis, about this axis, it will be rotates. Earth rotates. Okay, geostationary satellite revolve in equatorial plane of Earth. The height of geostationary satellite is how much? What is the height of geostationary satellite? Okay, the height of geostationary satellite is height of geostationary satellite. Height of geostationary satellite from surface of Earth. Earth is nearly 35,700 kilometers. Very large height. Very large height. 35,700 kilometers. Very large height. Okay, this height is very much greater than the radius of Earth. Okay, radius of Earth is only 6,400 kilometers. This is about geostationary satellite. When it will in one day, it will do full information of the Earth. It will take the photographs and everything. In while going around this from here to here in a half rotation, it will cover the half of the Earth. In the remaining full Earth is covered because it is revolving at large height. Now let us go for the uses of this geostationary satellite. What are the uses of the geostationary satellite? Why we are using this satellite? Why we should launch the satellites? Right? And the next one is the uses of satellite. Uses of geostationary satellite. Where we will use this geostationary satellite? You listen very carefully. I am going to explain the uses of the geostationary satellite. The first use is that to know the shape and size of Earth. Okay, it will also take the photographs. Okay, to know shape and size of Earth. What is the shape of the Earth? What is the size of Earth? That can be find out by using the satellite. This is the first use. And the next second use is that to study the upper layers of atmosphere. To study the upper layers of atmosphere of Earth. And third use of the satellite is it is to used in the television communication and cellular communication. It is used in television. Okay, we will see satellite through satellite we are sending nowadays. Okay, American channel also we will get that is possible through the satellite. Okay, signal sent to satellite, from the satellite distribute the signals to the as from the station signals send to the satellite distribute the signals throughout the world. Okay, it is used in television communication. Satellite is used in the television communication and also used in the cellular communication. Okay, television communication and cellular communication, mobile communication. Okay, right. Next one is the to know the minerals and natural resources present on the Earth. This satellite is used to know the it is used to know the minerals and natural resources present on the surface of Earth. Present on the surface of Earth. This is about geostationary satellite. And the next satellite is the polar satellite. What is a polar satellite? Right. What is a polar satellite? I am going to erase this. Right. Let us start the next one. Next one is the polar satellites. This satellite also revolves around the Earth. Then what is the polar satellite? Okay. And before going to start the polar satellites, I want to ask one question to you, that tell me what is the time period of geostationary satellite? This is the first question. And the second question is that how this satellite, how many revolutions can take by the satellite in one day? In one day, how many revolutions it takes? That is the one more question. Can you answer? Right, the polar satellite. You write in the chat box. A satellite revolves in polar orbit is called as polar satellite. Polar satellite means it is a satellite revolves a satellite revolves in polar orbit. Okay, polar orbit. A satellite revolves in polar orbit. In a polar orbit is called as polar satellite. It will revolve around the poles. How it will be revolves? Let us discuss with the diagram. Okay, this is the Earth. Up to 7 o'clock, I will continue the class. Okay. This is the two poles, right? Earth has the two poles. This is the axis of the Earth, right? This is the axis. Earth has two poles, north and south poles, right? This is the geographical north and this is the geographical south. And now this is the one pole of the Earth we tell. This is the another pole of the Earth. Earth will act as a magnet also. It has the two poles. Now our satellite revolves around the poles. Like this it will be revolves, right? You see here. Like this it will revolve. Now it will be revolves in around the poles like this. Its orbit is perpendicular to equatorial plane. Previously this geostationary satellite revolves like this, right? It is in the equatorial plane. This is in the right. It is in a plane that is perpendicular to the equatorial plane, right? And around the poles it will be revolves. This is the polar orbit. Now we draw the satellite. This is the satellite. Okay, the satellite speed is v naught. Mass is small m. This is the Earth. Earth mass is capital M and Earth radius is capital R. Okay, right. And now around the poles it will revolve. This satellite is called as the polar satellite. Now this satellite moves around the north and south poles of Earth. Okay, this satellite moves around the north and south poles of Earth. Okay, right. And the next one is, what is the time period of this satellite? Time period of polar satellite. Time period of polar satellite. Time period of polar satellite is only 100 minutes. 100 minutes means just nearly 1.5 hour, 1.5 hour. Just okay, within 1.5 hour, 60 minutes, 40 minutes. That means 1 hour, 40 minutes. Just 1 hour, 40 minutes. In 1 hour, 40 minutes, it will complete the one revolution. Okay, that means it will go fastly. But the geostationary satellite, it will complete in 24 hours. But the why it is completing very fastly means because it is rotating at very less height. The height of the polar satellite is in the range like this. The height of polar satellite is 500 to 800 kilometers. This is the height of polar satellite. Okay, right. And what are the uses of the polar satellite? Actually, what happens, the earth will revolve around about its own axis like this. Earth revolves like this. Is it right? About its own axis, it will be revolves like this. And when in 24 hours it will complete so many rotations, because in 1 hour only it is 1 hour 40 minutes, nearly 2 hours it is rotating one revolution. In 24 hours means in 24 hours, right, nearly it will in 1 hour 40 minutes it is completing how many, right, one revolution. And we have 24 hours in a day, right? Okay, nearly how many revolutions it will takes? Nearly 12 revolutions it will takes. Actually, in the first revolution, what happens? Little area is covered on the earth. This much, this patch of area is covered. When it will come in the second revolution, this will be goes this side. Why this will go this side? Because earth is rotating, na. Due to that, other area will come to here below the satellite. And next, in the third round of the satellite, third revolution of satellite, again this earth rotates, and again new area which is not covered, it will come under the satellite. Okay, like this what happens? For example, this is the satellite. Starting this area is covered. In the beginning, for example, this area is covered. Okay, in the first revolution, and the satellite covers this much area on the earth. After some time, what happens? This will go to here. After some time, the earth is rotating. That's why that area will go to here. When the area goes to other place, here the new area will comes in the second revolution. Okay, the new area will comes. That's why what happens? Then like this in one day, it will cover the all areas. In one day, it will cover the all areas like this. Okay, right. And next we will go for the uses of this satellite. Uses of polar satellite. What are the uses of this satellite? Now, uses of polar satellite. In one day, it will cover the full Earth. Right? But geostationary satellite, it will complete one revolution only in one day. In one revolution only, it will cover the total Earth because it is at very large height. But the polar satellite is at very less height. Okay, in one day, it also covers the total Earth surface. Now, let us go for the uses of polar satellite. Uses of polar satellite. What are the uses of the polar satellite? First one is that the polar satellite uses I am going to explain. Polar satellites are used in weather and environment monitoring. Okay, to know the weather changes, to forecast the weather changes, we will use this satellite. Okay, polar satellites are used to forecast the weather changes, used in weather and environment changes. Okay, environment monitoring. Monitoring means just what changes occurring in the environment that can be monitored. And the second point is that they are used in spying work of military purpose. They are also used for the military purpose. It will take the photographs on the earth's surface. Okay, and it is also used in the military purpose. These are the uses. And the next one more pending last topic is there, and with that I'm going to complete this chapter. Theory part I am going to complete, right? And within 5 minutes I am going to close. Next one is the Cavendish method. Cavendish method to determine capital G. Do you know what is the name of capital G? Do you know what is the name of capital G? Can anyone write in the chat box what is capital G? No one is giving the reply. Write in the chat box. Cavendish method. Cavendish is the name of the scientist. He find out one method to determine the capital G. That method I am going to explain. Okay. Right. For the purpose, this is a rigid support. From that, by using a string, I suspended one weightless thin rod. Okay. This its weight is negligible. Its length we will take as the 2L. Okay. And suspended at the middle. This side length L and this side length L. And two small masses are attached on both sides. This mass is small m and this is mass is small m. And now this is the weightless rod. We are suspending by using a string. String means wire. Okay, this is a string. And now for this, small masses are added on both sides. This is the mass small m and this is the mass small m that we are adding on both sides of the light rod. Then after that, what you have to do, you have to bring the large masses on in opposite direction. This is a mass capital M. You brought it at a distance smaller on one side. In the other opposite side again, you will bring one more mass that is also capital M, and you bring it a distance smaller in opposite direction. At that moment, what happens at here? This small m mass is attracted by this capital M this side force will act, and this capital M also attracts this small m that side because of gravitational force. Okay, and equal and opposite forces are acting on this thin rod. Okay, one side this one and other side that one. Due to this, it will be rotates. And now when it will be rotates by an angle theta, when it, for example, it is rotating by an angle theta like this, it is rotates. This rod will be rotates. Rod will be rotates like this. Why the rod is rotating at here? Because of okay, because of the torque. Equal and opposite forces are acting. And now due to this rotation, what happens at here? Some restoring torque is generated in this string. For example, if you left free these masses, you can remove. Just a rod you can suspend one by using a string. Just with your hand you rotate it like this, and then after that leave it. It will come back now again like this. Then the force you are rotating to a side. Then after that, if you will left free at this location, in itself it will come back and it will do some oscillations. The force which is trying to bring the uh, body to its original position is called as the restoring torque or the restoring force. Okay, here it is the for the rotating force is called as the torque. Okay, one here what happens, one this object is attracting this side, this object is attracting that side, equal and opposite forces are acting. That equal and opposite forces constitute the torque. Okay, torque or the, now let us see deflecting torque. In this, some torque will be deflect due to the attraction force, some torque will be generated in that restoring torque due to this elasticity property of string. Okay, in this case at equilibrium, for example, after rotating to this point at an angle theta, it is completely at rest, rod is at rest. Rod is at rest means deflecting torque. Deflecting torque means it will try to rotate it. The torque which rotates is called as a deflecting torque. The torque which not allows to rotate, it will try to bring back, that is called as a restoring torque. Okay, deflecting torque is due to the attraction of this force. This capital M is attracting this side, this capital M is attracting this side, this capital M attracts the small m this side, this capital M also attracts the small m that side. Equal and opposite forces makes to rotate this object, right? And now that is a deflecting torque. Deflecting torque is due to the attraction force. Now at equilibrium, what happens? Deflecting torque should be equal to the restoring torque. Okay, at equilibrium, deflecting torque is equal. Equilibrium means rest. Rest means torque should be zero. Okay, equal and opposite torque should be there. Deflecting torque is equal to restoring torque. Can anyone write the formula for the torque? What is the torque at here? Okay, torque is nothing but couple at here. Couple is the force into perpendicular distance between the forces. Otherwise, we can write the two torques will be there. One force is F and perpendicular distance of this one is L. This one force and perpendicular distance L. This side force F, perpendicular distance L. This is fixed point. Force into perpendicular distance. FL plus FL. Okay, 2FL. And restoring torque is what? Restoring torque for restoring torque per unit twist we can take as C. Let us consider C is the restoring torque per unit twist. Restoring torque per unit twist. Okay, within 2 minutes I am going to close. Unit twist means per 1 degree restoring torque is C. And for theta degree restoring torque, how much it will be there? Theta into C. Theta into C. That is nothing but C theta is the restoring torque. And we will get 2FL is equal to C theta. Okay. And F is what? F is the gravitational force between these two. That we write as according to universal gravitational law, GMM by R square we write into L is equal to C theta we write. From this, you can find out the here we have to write only one deflecting torque because this is the deflecting torque. This deflecting torque is the this side force into perpendicular distance of this one. We take only one F. Sorry, I wrote by mistake. Here we have to take only one force, right? And this is the formula. By using this formula, we can find out the G. Okay, by using above formula, we will determine Cavendish. Cavendish is the name of the scientist. He determined the capital G. We will determine the value of capital G. The practical value of capital G is 6.67 into 10 to the power of minus 11 Newton meter square per kg square. In this, L is the half of the length of the rod. Small m is the mass which is attached at the one end of the rod. Capital M is the huge mass that we are bringing on both sides. Small r is the distance between these two. Okay, and C is the restoring torque per unit twist. For you are suspending by using a string. That string has a restoring torque. It has certain constant restoring torque per unit twist. For 1 degree, how much restoring torque? It is rotated by some angle, that is theta. Right? By substituting all values, you will get the answer. Okay. Right. With this chapter is completed, and some problems we will discuss later based on these concepts. Okay, and I am going to close today's lecture. Thank you to all. Okay, Anshu, right? Universal gravitational constant. Good. Thank you to all. I am closing the lecture.